In this video, I'm going to show you how we can find double integrals by writing them in the form of product of two single integrals. Look at this first example. Integral from 0 to pi over 2, 0 to 2 of x cosine y dx dy. If you look at this function, x cosine y, let me name this f of x and y. So f of x and y is x cosine y. If you pay attention, this function is product of two parts, that one part is only in terms of x and the other part is only in terms of y. For this reason, for finding this integral, instead of integrating this function with respect to x first, evaluating the inner integral, then integrating the answer with respect to y, we can evaluate this integral in this form. We can write this as the product of two single integrals in this form. Attention, x is from 0 to 2, so we write integral 0 to 2 dx here. Which part of this function is in terms of x? X, so we have x dx. And for y, we have cosine y dy from 0 to pi over 2. So for finding this integral, we can write this double integral in the form of product of two single integrals. Now we have to find these integrals. Integral of x based on the power rule is x to the 2 over 2 from 0 to 2. And integral of cosine is sine of y from 0 to pi over 2. Now we have to substitute the values. If we plug in 2 for x, we have 2 to the 2, which is 4 over 2, minus if we plug in 0, we have 0 to the 2, which is 0 over 2, times this by, now plug in pi over 2 for y, sine of pi over 2, minus sine of 0. 4 over 2 is 2, 2 minus 0 is 2, so the first bracket is 2. Sine of pi over 2 is 1, sine of 0 is 0. So the second bracket is 1, so 2 times 1 is 2. And so the answer of this integral is 2. We can use this technique, attention, we can use this technique to write a double integral in the form of product of two single integrals for functions that the function that appears here is the product of two parts, that one part is only in terms of x and the other part is only in terms of y. Let me show you another example to understand this technique better. Integral from 1 to e, integral 1 to e of L of y over xy dy dx. The function that here we have is ln of y over xy. If you pay attention, this part is only in terms of x and this part is only in terms of y. So we can write this function in the form of, please attention, we can write this function in the form of 1 over x times ln of y over y. If you multiply numerator by numerator, this is the numerator, denominator by denominator, and this is the denominator. So we can write this function in the form of 1 over x, which is only in terms of x, times by ln of y over y, which is only in terms of y. So for finding this integral, we can write it as the product of two single integrals in this form. Integral 1 to e 1 over x dx or dy. You can write the part which is in terms of y here. Then you can write the term that is in terms of x. The order really doesn't matter because this is the product. And attention, the lower limit and the upper limit for x and y is the same in this case. So we have for x integral of 1 over x dx from 1 to e, and for y we have integral of ln of y over y dy. The first integral is very simple. Integral of 1 over x is ln of x or ln of absolute of x from 1 to e. What about the second integral? What is the integral of ln of y over y dy from 1 to e? This integral, with a simple u substitution, you can see that this integral equals 1/2 ln of y to the 2. Let me finish my calculation here, then I will show you how you can find this integral by u substitution. For now, suppose this is the answer of that integral. So integral of ln of y over y dy is 1/2 ln of y to the 2 from 1 to e. If we plug in e here, we have ln of e minus ln of 1 if we plug in 1 times y. Now in this expression we have plug in e and 1. If we substitute e, we have 1/2 ln of e to the power of 2 minus 1/2 ln of 1 to the 2. Ln of e is 1, so this is 1. Ln of 1 is 0. So all of this bracket is 1. So the first bracket is only 1. So here we have 1 time. What about second bracket? Ln of e again is 1. 1 to the 2 is 1. 1 times 1/2 is 1/2. Ln of 1 is 0, so all of this is 0, so minus 0. So the answer is 1 times 1/2, 1/2. So this is the final answer for this integral. Now let me show you how we can find integral of ln of y over y dy. For finding this integral, simply you can use a u substitution. If you suppose here u as ln of y, we suppose numerator as u, and the reason that it's a good idea to choose u as ln of y is because derivative of u or differential of u du is, what is du? If we take derivative, ln of y is 1 over y dy. If we solve this for dy, dy equals, from this relation dy equals y du. This is dy. Now let's do the substitution. Ln of y is u. Leave the y in the denominator. So far we have u over y. For dy, you can substitute dy with y du. So times y du. The y from numerator with denominator cancels. And then we have u du. So we have integral of u du. Integral of u du with the power rule is 1/2 u to the 2 plus c. But u is ln of y. So the answer is 1/2 ln of y to the 2 plus c. Exactly this answer which we had here. Now let me show you another example of finding a double integral with writing it as in the form of product of two single integrals. Look at this example. Integral from 0 to 1, integral from 0 to pi over 4, tangent theta over 1 plus u to the 2 d theta du. We can write tangent theta over 1 plus u to the 2 in the form of tangent theta times by 1 over 1 plus u to the 2. If you multiply tangent by this fraction, it's exactly this fraction. So it should be clear for you that we can write this function in this form. Now if you pay attention, we have written this function as product of two functions, that one of them is only in terms of theta, the other one is only in terms of u. So we can calculate this given integral, this double integral, with writing it in the form of product of two single integrals. So we write this in the form of integral 0 to 1 of 1 over 1 plus u to the 2 du times by integral 0 to pi over 4. Attention, these limits are for theta. So we have integral of tangent theta d theta. If you remember from integral formulas, integral of 1 over 1 plus u to the 2 is tangent inverse of u from 0 to 1. This is one of the formulas in the integral. What was integral of tangent? If you remember, integral of tangent is ln of secant. So if you don't remember this formula, or if you don't know how to calculate integral of tangent, I will explain how we can find integral of tangent after I finish my calculation here. For now, suppose integral of tangent theta is ln of secant theta from 0 to pi over 4. Now we have to do the substitution. If you plug in 1 in the tangent, we have tangent inverse of 1. So tangent inverse of 1 minus tangent inverse of 0 times this y. We plug in pi over 4, ln of secant of pi over 4 minus ln of absolute of secant of 0. Tangent inverse of 1 is pi over 4. Tangent inverse of 0 is 0. Secant of pi over 4. Secant of pi over 4 is basically 1 over, secant is 1 over cosine. 1 over cosine of pi over 4. If you remember from special triangles, we know that cosine of pi over 4 is 1 over radical 2. 1 over radical 2 is radical 2. So secant of pi over 4 is radical 2. So we have ln of radical 2. Secant of 0 is 1 over cosine of 0. 1 over cosine of 0 is 1, so 1 over 1 is 1. So we have ln of 1, but ln of 1 is 0. So ln of secant of 0 is 0. So we have only ln of radical 2 basically here. Now we have to multiply these two by each other. So this equals pi over 4 ln of radical 2. But if you like, you can write this answer in the form of pi over 8 ln of 2. Let me explain to you why you can write this answer in the form of pi over 8 ln of 2. Because pi over 4 ln of radical 2 is basically pi over 4 ln of 2 to the power of 1/2. If you bring this power to the front, we know that for logarithmic function, if we have a power here, we can bring it down to here. 1/2 times pi over 4 is exactly pi over 8. So if you want, you can write your answer in this form here. But it's okay to leave your answer in this form as well. Now let me explain to you how the integral of tangent is ln of secant of theta if you don't know the rule or formula. For finding integral of tangent theta d theta, attention, tangent is sine over cosine d theta. Now please attention. Whenever we have a fraction, this is very useful thing to know. Whenever we have a fraction, and please attention, if whatever is in the denominator, its derivative is in the numerator. So please let me repeat this again. Whenever we have a fraction like this, if the expression that is in the denominator, its derivative is in the numerator, then the integral of this expression is ln of the denominator. Let me give you an example so you understand this technique better. For example, suppose you want to find the integral of 2x over x2 plus 9 dx. Easily you can see that the derivative of the expression in the denominator is exactly in the numerator. When we have something like this, the answer is ln of the denominator. You don't need to do any u substitution to find these type of integrals. So whenever whatever is in the denominator, its derivative is exactly in numerator, then the answer of that integral is ln of whatever is in the denominator. Let me show you another example. What is integral of cosine theta over sine theta? The answer is ln of denominator, ln of sine of theta. Sine of theta. Because the derivative of the denominator is exactly in numerator. Now let's back to our question here. Here, what is derivative of denominator? Derivative of cosine is negative sine, but here we have only sine. We don't have negative sine. Okay, because we don't have negative sign, we can multiply the numerator by a negative. But because we multiply the numerator by negative, we have to add, basically we have to multiply the outside by a negative. So this negative with this negative cancels, so we changed nothing here. Now, derivative of the denominator now is exactly in the numerator, so the answer of this integral is negative, we put this negative here, ln of the denominator, ln of cosine theta plus c. Now, if we bring this negative, which is a coefficient for ln, to the power here, we have cosine to the power of -1. Cosine to the -1 is 1 over cosine, and 1 over cosine is secant, so this equals ln of secant theta plus c, which is exactly this expression. Now let me show you another example of finding double integrals by writing them in the form of product of two single integrals. Integral 0 to 1, integral 0 to 1 x y e to the x2 plus y dx dy. For this part, please attention, you can write e to the x2 plus y in the form of e to the x2 times e to the y. Because if we add the powers, these two powers, then we back to this. Now let me show you how we can find this integral. First, we write this in the form of integral 0 to 1 x e to the x2 dx integral 0 to 1 y e to the y dy. Again, please attention. If we multiply this by e to the y, e to the x2 times e to the y is e to the x2 plus y. So we can write this double integral as the product of two single integrals. Now we have to find these integrals. For the first one, for this one, with a simple u substitution, you can see that this integral equals 1/2 e to the x2 from 0 to 1. I will show you how you can find this integral with u substitution in a moment, but for now, suppose this is the answer. For the other integral, for this one, you can use integration by parts, and you can see that this integral equals y minus 1 e to the y from 0 to 1. Now the only thing that we have to do is substitution, the upper limit and lower limit. If you plug in 1, we have 1/2 e to the 1, which is e, minus, if we plug in 0 here, we have e to the 0, e to the 0 is 1, so we have only 1/2 times 1, which is 1/2. So this is for the first one. For the other one, if we plug in 1 here, 1 minus 1 is 0, so this is completely 0. So when we substitute 1, we get 0. Now we have to plug in 0 for y. 0 minus 1 is -1, e to the 0 is 1, so all of this is -1. And so the second bracket, this bracket is 1. Timed by this would be this again. So the final answer is 1/2 e minus 1/2. And if you like, you can write this in the form of 1/2 times e minus 1. If you factor 1/2 from these two terms, you can write this in this form as well. And this is the answer. Now let me show you how you can evaluate this integral with u substitution. For finding integral of x e to the x2 dx, simply you can use a u substitution. You can suppose u as x to the 2. Then from this du is 2x dx. And if you solve this for dx, dx equals du over 2x. Now if we do the substitution, we have x times e to the u, the exponent is u. Dx is du over 2x. If we cancel x with x, then we have 1/2 eu du. And if you put the 1/2 outside of the integral, we have EU du, and this equals 1/2 e to the u. But remember, the u is x to the 2, so this is 1/2 e to the x to the 2 plus c. What about this integral? For finding this integral, simply you can use u substitution method for finding this integral. For finding integral of y e to the y dy, you can suppose u as y, and you can suppose dv as e to the y dy. From this relation, from this one, du is dy. And from this relation, v, if we integrate from both sides, v is e to the y. Now we have everything ready for finding the answer of this integral. Let me remind you integration by parts formula. Integral of u dv is uv minus integral of v du. uv. What is uv here? uv equals y times e to the y. y e to the y minus integral of v, which is e to the y times du. du is dy. So we have ey dy. Let me erase these things from here. And as you can see, this equals y e to the y minus e to the y plus c. From these two terms, if you factor e to the y, then you have y minus 1 e to the y plus c, which is exactly this expression here. Also, for finding this integral, if you want to find this integral a little easier, you can use the table method, which is basically the integration by parts method, but it's a little simpler version of integration by parts method. And with that method also you can find this integral. If you want to learn about table method for finding integrals, you can watch my video for this topic. Let me show you one more example. Look at this example. Integral from 0 to 1, integral 0 to 3 of 1 over xy plus x plus y plus 1 dx dy. Let's see if we can find this integral by writing this expression in the form of product of two expressions, that one of them is only in terms of x, the other one is only in terms of y. If you pay attention, the expression in the denominator can be factored in the form of x plus 1 times y plus 1. If you multiply these two brackets by each other, you would get exactly this expression. X times y is xy, x times 1 is x, y times 1 is y, and 1 times 1 is 1. So we can factor the expression in the denominator, and we can write this integral in the form of integral 0 to 1, integral 0 to 3 of 1 over x plus 1 times y plus 1 dx dy. Now simply we can write this in the form of integral 0 to 1 for dy, integral 0 to 3 for dx. The part that is related to dy is 1 over y plus 1. The part related to x is 1 over x plus 1. Here, attention, because derivative of the bottom, derivative of the expression in the denominator is exactly in numerator, so the integral, the first integral is ln of the denominator, ln of y plus 1 from 0 to 1 times by ln of the denominator for this one. Ln of denominator is the answer of this integral from 0 to 3. Remember, I told you this technique. Whenever the derivative of the denominator is exactly in numerator, the answer of the integral is ln of the denominator. The derivative of the denominator is exactly 1, so the answer of this integral is ln of the denominator. Now we have to evaluate these expressions. The first one is, if we plug in 1 here, we have ln of 2. If we plug in 0 here, we have ln of 1. For the other one, we have ln of 3 plus 1 is 4. If we plug in 0, 0 plus 1 is 1, so ln of 1. For ln of 2, we have ln of 2. We don't know exact value for that, so we leave it as ln of 2. Ln of 1 is 0, so minus 0 times y. Ln of 4 is ln of 4 minus 0. So the answer is ln of 2 times ln of 4. But attention, ln of 4, because 4 is 2 to the 2, can be written as 2 ln of 2. So this equals ln of 2 times 2 ln of 2. And so this can be written as 2 times ln of 2 to the power of 2. Because ln of 2, when we multiply by ln of 2, it is ln of 2 to the 2. And with this 2 is exactly here. I hope by watching this video, you have learned how to evaluate double integrals in the form of the product of two single integrals whenever it is possible, of course. Not for all integrals we can do this. Whenever the function that we have here, the function that we want to integrate, is the product of two functions like this, is the product of two functions, that one of them is only in terms of x, the other one is only in terms of y, we can use this technique. And this is really helpful for finding double integrals or even triple integrals because it makes calculation easier. If you like this video, please subscribe to my channel and see you in the next videos.